Welcome to I Love Apes. My name is Eric Sampson, and what I want to do is help you get a 5 on your AP test. Now, today we're going to be looking at sunlight and seasons. It is a concept that is pretty important in AP Physics, and it's a little bit difficult to wrap your head around. So please pay close attention, and if you need to, rewind or look at the PDF of this document, because it is important and it is a little bit tricky. Let's go ahead and get started. So I'll ask you this to start with. Why is it hotter at noon than it is at sunrise? Well, there's a couple reasons, but the main one is this. It turns out that at noon, the sun's rays are coming pretty much straight down, and that means there's more light energy concentrated per unit of area. Each square meter of surface is receiving more light energy and converting it into heat. Whereas at sunrise, those same rays are coming in at a lower angle and getting spread out over a larger area, leaving less light energy per square meter of surface and therefore less heat energy per square unit of surface. Makes sense, right? Now, if we're going to talk about energy, we have to address this. We're going to measure energy in units of joules. And before you freak out, don't worry. We don't get too into the weeds with the physics of all this. But there will be things this year where we have to talk about energy. And of course, we have to talk about the units, which are joules. You've probably covered this in biology and in chemistry, but let's just get that out there. So when we're talking about energy from the sun arriving at Earth, we want to talk about something called the solar constant. So basically what this means is when the sun is directly overhead and shining down at 90 degrees to Earth's surface, we find that there are 1,361 joules of light energy arriving at each square meter of Earth's surface every second. Now, don't worry, this is not a number you have to memorize, but it's one we're going to reference in this video. So again, when the sun is shining straight down at 90 degrees to Earth's surface, perpendicular to Earth's surface, each square meter of the surface is going to receive 1,361 joules every second. We call this the solar constant. And the thing is, though, because we're talking about per second, per meter, it makes it a little bit tricky. So usually what we do instead is we convert joules per second to things called watts. So a watt, which is something I'm sure you've heard of when you talk about electronics, you talk about watts. Watt is a measure of power, and that basically just means how much energy is converted every second. And again, don't get too worried about this. We don't have to get too caught up in this, but just know that 1 joule per second is referred to as 1 watt of power. And so therefore 1 watt is just the equivalent to 1 joule per second. And so the solar constant therefore is usually referenced this way, is 1,361 watts per square meter. So let's take a look at what this means. Here I have the Earth, I have the sun, and what I'm going to do is I'm going to position a panel, a solar panel, that's 1 square meter in area, and I'm going to position it at the equator. Now, as energy arrives from the sun, there's going to be 1,361 joules arriving every second on that square meter, so I'm going to record a power of 1,361 watts per square meter, which is the solar constant. Now, if I take an identical solar panel and I position it at the North Pole, as long as I also orient it so it's oriented perpendicular to the sun's rays, I'm going to get the same value. That's why this is called the solar constant, because at Earth's distance from the sun, this is how much energy arrives. And it is a constant. It doesn't change from day to day, which is a good thing, because if it did, it would probably make life unsustainable on Earth. So let's think of it this way to try to help you understand the role of this angle in terms of the heat energy on Earth. So let's just say I had a solar constant flashlight. I'm just going to round it to 1,300 watts just to make my life a little bit easier. If I shine it straight down on Earth, it makes a 1 square meter circular patch, and I'll find that there's 1,300 watts arriving at every square meter when I have it oriented perpendicular to the surface. But if I then take it and tip it at 30 degrees, what I'll find is that spot is now going to be 2 square meters instead of 1 square meter, and that means each square meter is going to receive half as much energy. So instead of it being 1,300 watts per square meter, it's only going to be 650 watts per square meter. So I put a solar panel here. It receives the solar constant, right, because it's perpendicular to the sun's rays. But the thing is, last time I put this solar panel up here perpendicular to the sun's rays, but the surface of the Earth is curved, and so it's really only perpendicular to it here at the equator, the way this is drawn here. Now, if I put it up here, I'd find that it's actually at an angle. And I put it here so it's about a 30-degree angle. So I'd find is, instead of getting 1361 watts per square meter, I'm going to get about half as much. So there's less light energy arriving here because it's spread out over a greater area, like I showed you with that flashlight. What this tells us then is at the equator, light comes down at a steeper angle, so its rays are concentrated in a smaller area, and that tends to make it hotter because there's more energy getting converted to heat per unit of surface area. Whereas near the poles, that same light is getting spread out over a larger area, leaving less light energy converted to heat per square meter, so of course it's going to be colder. Another thing to keep in mind, though, is because the sun's rays are concentrated near the equator, that means there's more light arriving, and instead of being converted to heat, what about being converted to glucose? So what we're going to find is that NPP is higher at the equator because light is more concentrated, at least in part because of that. And if we go to higher latitudes, farther away from the equator and closer to the poles, we're going to find that the NPP tends to be lower because there's less light energy arriving per square meter in order for plants to access. Now, this next part is where it gets a little bit tricky. Okay, you ready? So if Earth's rotational axis that we spin around on, that goes to the north and south pole, if that was oriented 90 degrees to the circular path that the Earth takes as it orbits the sun, we would get 12 hours of daylight and 12 hours of darkness every day. So let's just look at this. So I'm saying if this was the case, then I have on June 21, I have the Earth here, and these dates are chosen for a reason. You'll see in a minute. But what's going to happen is as it goes around halfway through the year, it's now over here. It's September 22, and then it's over here. It's December 21, and then it's over here. It's March 20. Now notice this is supposed to be darkness. So the sunlight comes here. Here's daylight. Here's darkness. You can see that's half the day is light, half the day is dark. And over here, I'm seeing only the sunny side of it. Here, I'm seeing here's the sunny side, here's the dark side. And here, I'm looking at it from the back, so I'm only seeing the nighttime. Now, let's just zoom in on this a little bit and try to get a sense of this. So if Earth's axis is rotated perpendicular to the orbital path, everywhere on Earth gets 12 hours of daylight and 12 hours of darkness every 24 hours. Because look at this. I'm just going to go across here as I orbit around. So if I'm standing here, I'm going to circle around the Earth. And you'll notice half the time I'm in darkness, half the time I'm in light. Half the time I'm in light, half the time I'm in darkness. Half the time light, half the time, no matter where you are. But it turns out the Earth's rotational axis is not 90 degrees to Earth's orbital path, but rather it is oriented at 23.5 degrees to its orbital path. So let's just take a look what that does. So here we are on June 21, and instead of the axis being tipped this way, perpendicular to the orbital path, it's actually tipped 23.5 degrees this way. So the northern axis is tipped towards the sun, and the southern one is tipped 23.5 degrees away from the sun. And this is why we get changes in seasonal daylight hours and temperature over the course of the year. So let's follow the Earth around for 1 year. So we started June 21, we come over to here, now it is September 22nd, and at this point, this axis is tipped neither towards nor away from the sun. And then if I keep going around, I find that at December 21, the northern hemisphere is now tipped 23.5 degrees away from the sun, and it's the southern axis that's tipped 23.5 degrees towards the sun. And as I come around to March, on March 20, I find that, and I'm looking at the nighttime part of the Earth, I find that this axis is neither tipped towards nor away, and as we move this way, it gets tipped more and more and more towards, the northern part more and more towards, and we move into summertime. So on the June solstice, this is the orientation of the Earth. And what I would find is that in the northern hemisphere, the days are going to be longer than the nights. So I notice as I go across here, as I orbit the Earth, as the Earth spins on its axis, what I'm going to find is that the nights are short and the days are longer. And the farther I get away from the equator, the more extreme that is. So here I find that I have very little bit of night and an awful lot of day. And if I get to a thing called the Arctic Circle, I notice that there's 24 hours of daylight here. And if I come down here into the Antarctic Circle, I find that there's 24 hours of darkness here. Well, let's look at the December solstice. So in December 21, we're tipped 23.5 degrees in this orientation, so that the north is 23.5 degrees away from the sun, and the south is 23.5 degrees towards the sun. So what does that do? So here I've got it so that I see in the northern hemisphere, what I'll find is my days are short and my nights are long. In fact, if I go to the Arctic Circle, there's 24 hours of darkness, which is the opposite of what happened at the June solstice. And again, as I move towards the equator, the difference is still there. It's just not as extreme. The days are still longer than the nights, but not by as much. And when I get to the equator, 12 hours of daylight, 12 hours of darkness. Now when I move into the southern hemisphere, it is their summertime. And so what I find is that their days are longer than their nights. And if I get all the way to the Antarctic Circle, someone there is going to experience 24 hours of daylight. Okay, so let's consider this. On the June solstice, the northern hemisphere is tipped 23.5 degrees towards the sun, and that means there's more daylight hours than there is darkness. But on the December solstice, the northern axis is tipped 23.5 degrees away from the sun, so there's more darkness than there is daylight. Well, if you think about it, there has to be a point of transition between those two, right? So it turns out on September 22, there is a moment where there is exactly 12 hours of daylight and 12 hours of darkness. Here the days were longer, here the days were shorter, here the days were equal, and so we have the term equinox to refer to this date. So the equinox, which comes from the Latin for equal night, basically means that the days and the nights are of equal length, and that happens on September 22, and it happens again on March 20th. So if you think about it, here in the north, the nights are longer than the day, and what happens is the days are getting longer and longer and longer, but they're still less than the night, right? But when I get to here, I have 12 hours of light, 12 hours of darkness, and once I get to here, the days become longer than the nights until I get to my longest day on June 21. Now, the seasonal changes in the orientation of Earth's axis cause something even more important, and that is a change in the height of the sun above the horizon, which makes the rays of light more direct or less direct, and that changes how much light is arriving at Earth's surface, and therefore how much productivity you can have and what the temperature is going to be. So first, to wrap your head around it, it's best to think about it on the day of the equinox. So here I have a number of people, I think it was 5 people, scattered around the Earth on the day of the equinox. So I have a person at the North Pole, a person at the South Pole, a person at the equator, a person that is 23.5 degrees, and I chose that reason for a purpose, obviously, north of the equator, and a person who's 50 degrees south of the equator. So let's start with a person at the equator. The person at the equator at noon on the equinox is going to find at noon the sun is directly overhead. It's coming down 90 degrees perpendicular to Earth's surface. So here's a sweet trick. On the equinox, this works. You simply take the person's latitude, and the equator is considered to be latitude 0, and subtract it from 90, and that will tell you how high in the sky the sun is at noon. So 90 minus 0 is 90. Right? Well, let's look at the person who is 50 degrees south of the equator. So if I say 90 minus 50, what do I get? I get 40 degrees. So the sun would be 40 degrees above the northern horizon because they're south of the equator, so they're going to see the sun in the north. So that's how high it would be at noon on the equinox for that person. For the person who's at the South Pole, the sun is just going to barely graze the horizon on that because 90 minus 90 gives me 0 degrees. Well, let's go north of the equator. So this person is 23.5 degrees north of the equator. So if I say 90 minus 23.5, I get 66.5. So this person sees the sun quite high in the sky, but not 90 degrees overhead. And then if I go up here to the person at the North Pole, again, 90 minus 90 is 0. The sun is just barely grazing the horizon on this day. So let's now see what happens if we move forward in time to the June solstice. So on the June solstice, I've taken the whole situation and I've rotated 23.5 degrees this way. So this person who was at 90 degrees is now tipped 23.5 degrees forward. Everybody has been. So what does this do? So this person who had seen it at 0 degrees will now see it 23.5 degrees above the southern horizon, whereas before it was at 0 degrees. Now remember, this person saw it at 66.5, but I rotated them 23.5 degrees, so it's going to be higher in the sky by 23.5 degrees. They will see it 90 degrees above. So a person who started off 23.5 degrees above the horizon, on the day of the June solstice, will see the sun directly overhead. And then if I look at the person who was at the equator, on this day, they're not getting direct sunlight. The sun here is going to be 66.5 degrees above the northern horizon. And if I move down here and look at this person here, I'm going to find the sun is only 16.5. I take what it was before, which was 40, and I take 23.5 away from that, and here's what I get. They're still seeing the sun, but not a lot of it. And this person here, they're not going to see the sun at all. They're inside the Antarctic Circle, and during the June solstice, they're not going to see sunlight at all. And now the exact same thing is true in reverse if we were to go to the December solstice, but I don't want to work all the way through that as the video is long enough. So here's the big takeaway. Ready? So at the summer solstice, what we're going to find is, in the summer solstice, the sun is going to be 23.5 degrees higher at noon than it was at equinox. So that means the sun's rays are more direct, so there's more heat energy, there's more productivity, and also the daylight is longer. The sun is up for longer. So that combination of more concentrated light and longer time of light makes it hotter and more productive. Whereas in the winter months, what we're going to find is that the sun is 23.5 degrees lower in the sky than it was at equinox, which means the sun's light is more spread out and less concentrated, and the sun is up for less time. And that makes it colder, and it reduces plant productivity. Now, there's a few points on Earth that I've referenced some of them, but let's just talk about it. So the tropics, we've all heard about the tropics. What makes the tropic? Okay, the tropics are warm, the tropics are fun, the tropics are beautiful. Well, what does the tropic really mean? It means any region that is located within 23.5 degrees of the equator. So if I go 23.5 degrees north of the equator, I get the Tropic of Cancer. And you don't have to memorize that. If I go 23.5 degrees south of that, I have the Tropic of Capricorn. Now, what's special about that is we remember the previous slide, if you live in this region here, there's going to be at least one day, and if you're at the actual tropic line, but if you're within the tropic line, there's going to be 2 days of the year where the sun is directly overhead at noon. The Arctic Circle and Antarctic circles are special because in these regions here, you're within 23.5 degrees of the pole. So if you're within 23.5 degrees of the pole, there'll be one time during the year where you have 24 hours of darkness, and at least one time during the year where you have 24 hours of daylight. Hey, thanks for watching. Listen, if you found this video to be useful at all, I would appreciate if you go ahead and give it a like. If there's something you want to tell me, some kind of feedback or some video you'd like me to make, go ahead and put that in the comment section for me. Be sure to check the description below. I often post the PDF of the document that I use, also practice problems and so on that can help you do better on your AP test. And of course, you know what's coming. More than anything else, what I really need you to do is hit that subscribe button.